Assalamu alaikum everyone. I am Muhammad Arsalan and now we are going to start our module 7 that is current and electricity. The topics that we are going to cover today are shown on your screens. These topics and these learning outcomes are exactly the same that are mentioned in the syllabus document provided by the PMC about MDCAT. Okay. So let's start our first topic, that is electric current. So electric current is defined as the rate of flow of charge. Okay, the delta Q over here in this formula is representing change in charge, whereas delta T is representing change in time. So dividing these two quantities, delta Q by delta T, will give you the amount of current flowing. Okay, the unit for measurement of electric current is amperes or amps. 1 ampere is equal to 1 coulomb divided by 1 second. So 1 coulomb per second equals 1 amperes. Electric current is a scalar quantity. If you want to measure electric current in a circuit, then make sure to connect ammeter in series with the device in which you want to measure the current. Okay. For instance, let's consider that this figure in which you want to measure the current through the lamp. So we have to connect ammeter in series. Okay, conductors, specifically metal conductors, have sufficient quantity, in fact very large quantity of mobile or free electrons. However, in the absence of any external force or source, these electrons move haphazardly and they show a to and fro motion about their mean position. This happens because of their thermal energy. However, they do not actually move from, let's say, one end of conductor to the other end. That is why we can say that their average displacement is equal to 0. However, as we want electric charges to flow, because that's how our current is going to flow, so we have to provide some external source to make those charges and to force those charges to flow throughout the conductor. So we can do that by applying an external electric field. Okay, so what happens is this electric field energizes the electrons and pushes them across the conductor. So without electric field, electrons just move to and fro and their mean displacement is equal to 0. However, in the presence of electric field, electrons move in the direction of electric field. So the power supply in the figure is actually providing you the electric field. The positive terminal of the battery is connected to one end of the conductor and the negative is connected to other end. So electrons carry negative charge, hence they are attracted towards that end of conductor where positive terminal of battery is connected. So as a result, electrons will start drifting towards that end of conductor, and that is in the direction of electric field. So the velocity with which the electrons are moving in the presence of electric field is called drift velocity, and the typical value of drift velocity is about 10 raised to power minus 3 meters per second. Okay, so now let's move on to Ohm's law. Ohm's law states that the electric current flowing through a conductor is directly proportional to the applied voltage across it. Simply means that the current flowing inside a conductor is directly proportional to the applied voltage. However, make sure that the physical conditions such as the shape of conductor or temperature of conductor, etc., these are constant. Okay. If we plot the current versus voltage graph, we are going to get a straight line, as it can be observed in the figure over here on the screens. Okay, the gradient or slope of this curve is called 1 over R, where R is the resistance. So it's basically the constant of proportionality, and resistance is equal to voltage over current. It's simply by if I equals to V over R or V equals to IR, by using simple that relation. Okay, so the ohmic conductors are the conductors that follow the Ohm's law. Okay, so ohmic conductors are those conductors that follow Ohm's law. Okay, simply. So the resistance of a wire depends on the length of that wire. It also depends on the area of cross section, but it inversely depends on the area of cross section of that wire. Similarly, the resistance depends directly on the resistivity of the wire. Okay, the row over here in this formula that you can see on the screens represent the resistivity of the wire, of the material of the wire. Okay, so the resistivity of the material is equal to the resistance times cross sectional area divided by length, and its unit is ohm meter. So if a number of resistances are connected in series, as we can see in the figure, R1, R2 and R3 are connected in series, then the equivalent resistance of this combination of resistance, for instance, the total resistance that we can experience from between this terminal and this terminal, okay, the total resistance is equal to the sum of individual resistances. Such combination of resistances is obviously called series combination of resistance, and I repeat again, in series combination of resistance, total resistance is equal to the sum of individual resistances. Similarly, we have another, we can connect resistances in another combination, that is the parallel combination, and in parallel combination the inverse of the sum of the inverse of individual resistances is equal to the inverse of the equivalent resistance. That means that 1 over Req equals to 1 over R1 plus 1 over R2 plus 1 over R3, because we are using 3 resistances in our case. Okay, a very important property of the material, specifically the material which we are the conductor material, okay, is the temperature coefficient of resistance of that material. It is represented by alpha, and alpha equals to RT minus R naught or R0 divided by R0 times T, where alpha is the temperature coefficient of resistance of that material. RT is the resistance of that material at temperature T degree C or T kelvins. Okay, we can use both things, but we can use either degree Celsius scale, or we can also use Kelvin scale. Okay, so over here this RT is the temperature of the material, resistance of the material at T degree C or T kelvins. Okay, and this R0 is the resistance of the material at 0 degree C. Okay, by rearranging this formula we can get RT equals to R0 times 1 plus alpha T. So let's say we have a question in which we are asked to calculate or to find out the resistance at a particular temperature, whereas the reference resistor at is given the resistance value of the material at 0 degree C. So we can use this formula to calculate that resistance. Similarly, if instead of 0 degree C we are given some other reference temperature value, then this formula is not going to be applicable over there. In such a scenario, we have to use this second formula, which is that R2 equals to R1 times 1 plus alpha times T2 minus T1, where R2 is the resistance at temperature T2 and R1 is the resistance at temperature T1. Okay. So let's say you have T2, T1 and R1, the values T2, T1 and R1 are given, so you can easily calculate the value of R2 by using this formula. So by using this formula we can actually calculate we can calculate the value of resistance at any temperature of a given material, provided that reference temperature values as well as the reference resistance values are at those temperature is given to you. Okay, so next thing is the unit of temperature coefficient of resistance is per Kelvin or per degree Celsius. Similarly, another very important property of the conducting material is the temperature coefficient of resistivity. So first one was temperature coefficient of resistance. The second one is the temperature coefficient of resistivity, and it is represented by beta, and that is equal to sigma rho t minus rho 0 divided by rho 0 times t. This rho t is the resistivity at temperature T degree C, and rho 0 is the resistivity at 0 degree C. Okay, and its unit is also per Kelvin or per degree Celsius. By the way, we can devise similar formulas as shown over here in this equation by rearranging this equation. Okay, so these formulas are very important for the case of MCQs. Okay. So let's now study about electromotive force. Electromotive force is actually the energy transferred from other forms to electrical energy when a unit charge moves around a circuit. So this is the energy that actually pushes a unit charge throughout the circuit. Okay, that is equal to the work done on unit charge. So you can see the formula: EMF equals to work done divided by Q. So W is the work done on the charge Q. Okay, and potential difference and EMF actually are not the same thing. Okay, so what is the difference between them is this, that the EMF is the amount of energy given to each coulomb of charge so that it flows through the external circuit. However, potential difference is just the amount of energy utilized by 1 coulomb of charge. Okay, so EMF is actually the cause. EMF is the reason because of which a unit charge or electrons actually move in throughout the circuit, around the circuit. However, potential difference is its effect. Simply, without EMF there will be no potential difference. Okay, so so EMF exists with or without external circuit, but if there is no external circuit, then potential difference will be between any 2 points in a circuit. If the EMF source is disconnected, then the potential difference will be 0. Okay, between any 2 points in an external circuit. So I repeat again that if EMF exists only, then potential difference is going to exist. However, if you disconnect a circuit from the EMF source, then the potential difference between any 2 points in that external circuit is going to be equal to 0, because the power source, the EMF source, is actually being has been disconnected. Okay. So every realistic power source has an embedded internal resistance. So consider a battery, for example. A battery is made up of electrodes and some chemical material, that is so because some chemical reaction is going to take place inside a battery, so that energy is produced that actually helps the flow of electrons throughout the circuit. Okay, so a battery is made up of electrodes of different kinds of different material and some chemical stuff that is being stuffed inside that battery. Okay, so each of this material has different resistivity. Okay, because it's a realistic material, that's why there will be some internal resistance offered to the electrons or the charged particles being flown out of the battery. This internal resistance is going to cause some energy loss in the power source itself. Okay, so we can consider this example. So over here we can see that the EMF is the electromotive force, which is actually pushing the charged particles throughout the circuit, where R internal is representing the internal resistance of the battery. Okay, and the R load is, let's say, the output load, or you can say it may be a lamp, or it can be maybe a fan or some other electrical appliance. Okay, it's represented by R load. So we can see that EMF is actually equal to the voltage across R internal plus voltage across R load. Okay, and since R internal and R load are actually connected in series, so in series combination, the current through these resistances are going to be same. So we can write that EMF equals to I times R load plus I times R internal. Okay, so from here we can get the idea that when the load is disconnected, okay, when that means that I will be equal to 0. So when load is disconnected, I will be equal to 0. So when I equals to 0, then EMF will become equal to the battery output voltage. That means if we connect a voltmeter across the battery terminals, we will get the exact value of EMF in that scenario. So sometimes we also call V load as the terminal potential difference of battery. V load as the terminal potential difference of battery. Okay, and this is our last topic for this module, electric power. Okay, so electric power is the time rate by which electric energy is transferred in a circuit. So simply we know that the power is represented as work done divided by per unit time. Okay, so E over here is representing as energy or work done, and divided by T, and T is representing as time. Okay, now we also know that the energy for electric circuits is equal to voltage times charge. Voltage is representing the potential difference that is experienced by the charge Q. Okay, that is equal to the energy or work done on a charge. So if we substitute this E equals to VQ on the previous equation, we will get power equals to VQ divided by T. Over here we can we do know that charge divided by time, or change in charge divided by change in time, actually represents current. Okay, so from that we can deduce this result that electric power is equal to voltage times current. So if a potential difference is applied across, let's say, some appliance, and current is flowing through that appliance, then the power dissipated, the power consumed by that appliance will be equal to the voltage times the current. Voltage across that appliance multiplied by the current flowing through that appliance. Okay, considering this circuit again, we can actually calculate the power output, or we can say that the power across the power dissipated or consumed in the load resistor. Okay, for that we have to use the Kirchhoff's voltage divider rule. Okay, and then we have to calculate the power using the formula P equals to VI across the load resistance. Okay, we can easily reach at this result if we consider that R load minus R internal whole square equals to R load square plus R internal square minus twice of R load R internal. Okay, this if we solve this equation, then it will actually become equal to R load plus R internal square, and basically this is another form of this equation. So we can write this P equals to VI as P equals to V square over R, because I equals to what? So since we know by Ohm's law V equals to IR, okay, that means I equals to V divided by R. So if we replace this I by V by R, then we will get P equals to V square over R. Okay, so using this formula and this formula, we can easily reach to this result. So this result is also very important because it actually it tells you, and it actually informs you that what is the relation between R load and R internal in terms of the output power. So in this equation, in this expression, we can clearly see that we will get maximum output power when this factor becomes equal to 0, and this factor will become equals to 0 when R load becomes equal to R internal, and that is the condition for maximum power output. It occurs when the load resistance becomes equal to the internal resistance, and the maximum power that you can draw from any power source is equal to the EMF square divided by 4 times load resistance. Okay, we can exactly, in fact, we can replace this load resistor by R internal as well, because R load and R internal are equal to 0. So maximum power will occur when R load becomes equal to R internal. Okay. Lastly, the amount of energy consumed by an appliance of power rating or power requirement of 1000 watt, if it kept running for 1 hour, is equal to 1 kilowatt hour. That is the definition of 1 kilowatt hour. This is the unit by which our electricity consumption is being measured by the, for instance, in Pakistan it is being measured by the WAPDA or the or some, maybe if you are talking about the distribution companies, and we have Lesco or ISCO or other such companies. Okay, so they use this unit to actually measure the amount of electricity that is being consumed in our homes. Okay, so 1 kilowatt hour is equal to what? 1000 watt. An appliance, if an appliance having a power rating of 1000 watts is kept running for continuously for 1 hour, then the energy utilized by that appliance will be equal to 1 kilowatt or 1 unit of energy. Okay, that is equal to 3600 kilojoules or 3.6 megajoules. Okay, that is the 1 kilowatt energy. Okay. Okay, so lastly, our topic of electric current is now over. Current electricity, sorry, is over. But now it's very important. This thing is very important to discuss. Instead of having slides, we can have these important notes that are being made by Tabir Academy. Okay, so we are going to review the same topics from this Tabir Academy notes, and you can have them. I believe so that they are in fact readily available to you guys as well. So all the concepts that we have discussed and we have reviewed are actually mentioned in detail in this document. Okay, so the electric current, its formula, its units, it's the relation of ampere with coulomb and second. Similarly, the electric current in a wire and the drift velocity, the concept of drift velocity along with the Ohm's law. Okay, everything is written in detail in this document. So you can actually review these topics, because these topics are also the ones that are shared by the Pakistan Medical Commission's course outline for MDCAT. Okay, so these topics were extracted and written comprehensively, very comprehensively in these physics notes. Okay, so then we have this resistance of a wire, the R equals to rho L over A, and the combination of resistances, resistivity formula, and the temperature coefficient of resistance, and the temperature coefficient of resistivity. This is again very important. Then we have electromotive force, internal resistance, electric power, and the maximum power output along with the kilowatt hours. Okay, so you can have these notes and make sure to study and prepare yourself by utilizing these notes. Okay, so let's end this lecture and we will start our new lecture shortly.